We still have to talk in mathematical terms. But I want to tell an interesting story. Now that we have this equation, this fundamental equation of thermodynamics, I'll write it down one more time. And let's just break it down. Finally, that the change in internal energy of a system can be balanced by three different terms in chemistry. One is the entropic term, TdS. We have the pressure term, PdV, with a negative sign. We'll talk about why that has a negative sign. If I forget, just mention it to me. I'll try to justify it at some point for you. You should be able to do it today. Times the chemical potential times the change in the number of particles. Okay, this is Gibbs's equation. Fundamental relation. Different names for it, but mostly associated. And this basically says that when the again, you can think of it the right side or the left side. How you think about reaction, how you think about cause and effect here, it doesn't really matter. But the way I like to think about it is that our box is being tracked by this number U, which is the total energy. It's just a number that quantifies the total energy content. We can't really measure it, but we can measure changes in it extremely accurate. And the changes are divvied up in three different components. One is the change in entropy, this change in the motions that are being averaged out, all the random motions. We'll define it more carefully today. And then it's this pressure dependent term, which has something to do with the stretching motions of our gas pressing against the walls and how that gets affected. We change the volume of our system and it affects the energy. And then if we have some process that's exchanging molecules, say from one space to another, or you have a reservoir of some molecules that are exchanging with another reservoir of molecules, there might be some concentration gradients, difference in concentration or number density between two components of the box. And this tells you how energetically favorable for that concentration gradient to occur. So we have something like concentration gradient, something like pressure and volume, and then this entropic term that is a little, what's the word I'm looking for? A little opaque. It's not really clear what it represents. So what I want to talk about today, kind of our goal for the next couple of weeks, is to understand entropy as physically possible, as much as possible. So we've come up with this mathematical abstraction that tracks basically all the energy that isn't something orderly, right? Motion of atoms or changing of volume, those are very orderly motions. Changing the parameter space in your system. We have something else, all the other junk flowing around. So I kind of want to understand this from a more, well, one, we're going to understand it from a very qualitative perspective, tackle it qualitatively. And then what we'll do over the next couple of weeks, next week or so, is to think about it statistically. Use statistics to understand entropy. And this tracks with history. An intuitive understanding of what entropy is, and then there's a statistical understanding of entropy. They give you the same result, but one gives you a really like easy qualitative picture, and the other one gives you a very, very strong quantitative grasp. One gives you a direct way to calculate, and the other one gives you a way to understand. So I'm going to tell you a little story. Well, where does this
recording?
Yes. I set it up now to record automatically.
Okay.
Thank you. That's okay. Thank you for asking. I'll never be annoyed by that question because I'm very forgetful. So this is an experiment that came from Henry Joule, the namesake of the energy formula, or not the energy formula, the energy unit. Henry Joule. This is like early 1800s. Henry Joule does a very, very simple experiment. He wants to understand the nature of energy. This is right around the rise of first of all, modern chemistry. Modern chemistry was basically developed in the 1740s to the 1780s in France. And Henry Joule was following off of this in England, starting to think about chemistry from the point of view of energy. And Henry wants to, again, this is the Industrial Revolution, so everything is about engines and doing things with machines and combustion and steam and things like that. And Henry Joule notices, that there are in some sense, two different types of energy that he can touch and feel, two different processes that give you two different outputs that are in some sense completely different from each other. Right? One thing he sees that there's in some sense two different forms of energy. Right? One of those forms of energy is, imagine you have a water mill. Right? Where water is draining off of it, off of something, and pushing this wheel around. You've got water dripping off this wheel and pushing the wheel, like in a water mill. And of course, that water mill drives something else, right? That water mill uses that rotating power to drive a motor or a spindle or something, right? Some engine, right? Some device. So like a device or a grinder, or what do you call it? Like a mill, right? You're milling flour and you're using the grinder as being driven by the motion of this wheel. Right? So so there's some energy being transferred in some sense from this water through the wheel and into the mill to drive the mill. Right? So Joule notices again that you have the force of water acting on this wheel, which is giving the wheel some angular momentum. Right? It's giving the wheel some angular momentum, some angular velocity, and that's giving the system energy to drive the mill. Right? So energy, in some sense, is flowing from the water to the mill. Right? So water is used. So what we would say is that the gravitational force of water is driving the water wheel, creating energy. Of course, it's not really creating energy, but rather you're converting gravitational potential energy of the water into mechanical force, into mechanical. Right? This is a mechanical. Right? So he says, okay, well, I can do this process in the mill using this mechanical energy, which he labels work. So the term for this type of energy is called work. We label W, sometimes lowercase w, which is just mechanical energy, right? We are using the forces of Newton using Newtonian type forces, pushing and pulling to transfer energy and generate energy as work. Yeah, so there's work. But there's another way to drive the mill, right? What he could do instead is take a beaker, very, very simply. We'll take a beaker, fill it with some water, right, and then heat it. Right, you get some heat. Right, and what does that do? It boils the water. Right, you get boiling. And what you do is you condense that steam vapor into a tube, right? And you pressurize it, this tube. Right. And then you drive another wheel with that steam. That steam pressure, right? You have this flow of gas pressing down on this mill, which then drives the same mill again. Right? Now, the steam is doing work on the what do you call it? Sorry, on the material, on the wheel, right? It's still doing work. It's pushing the wheel with a pressure differential. It's pressing down on the wheel to push it. right? But that energy source is not from gravitational energy. It's not from the falling, right? The physical mechanical motion of water falling, but rather it's the pressure being built from the heat and the steam of the heat of the steam, right? So what he's doing is he's taking heat instead and driving this wheel using heat. So he says, okay, well, there's another type of energy, right? And of course, heat has to be used to boil the water, right? So that's a very obvious, it's not work being done at all. There is no mechanical work when you have just a thing of water and a heat and a fire, right? That's all heat. But it generates some energy and generates steam, which then does work for you, right? So there's this other type of energy that's completely different, or at least to early scientists, right? Which is the energy that's not mechanical. Right, and it has to do, obviously, it has to do with some temperature difference, right? It seems to be associated with differences in temperature, hot and cold. You can do work without everything being room temperature, right? This whole system is at the temperature of the water. We're still generating energy through mechanical energy. But here we have some cold, hot water in a cold mill, right? We have some gradient of temperature, and that's causing this heat being generated, and that heat is generating energy, which is driving the mill. So two different types of energy, heat versus work, right? And Joule labels heat with a different number. He doesn't use H, unfortunately. So heat, we often use the label Q for heat. And I think all of you have a very intuitive sense of this. This is a really logical way to split energy. Energy that's being done by pushing and pulling, physical forces, and then heat energy, which again, it's very opaque. It's not really clear what that means. It's just things that aren't mechanical. Up until Henry Joule, everyone thought these were two different sources of energy. The two completely orthogonal concepts. Heat and mechanical energy are generated differently, obviously, and therefore they are made in some sense of different stuff. The heat energy is different than mechanical energy. Right? That may seem really, really stupid to you, and it should, because they were wrong, very, very wrong. But that's a good question, right? Are they truly different, or what they're saying? Are they the same? So Henry Joule comes up with a really, really simple experiment. And this is an experiment you can do at home. Right, he takes a big dish of water. And inside that dish, he puts another dish of water with ice in it. Right, so you can imagine I'm putting a beaker inside of a dish. Okay. And inside of that dish, I'll try to kind of color it a little bit to distinguish it. Inside of this is some pieces of ice. This is ice water. And it's got some nasty green slushy ice water. And we keep the bath at some temperature. We can heat it, we can lower it, we can cool it, whatever we want. But let's just say, for instance, it's at 298 Kelvin. And this water initially is at 273 Kelvin. It's right, let's say 274, right above freezing the water. Okay, and what he does is he places a little spinning wheel, I don't know what you call it, it's a little turbine inside the slushy water. He puts a turbine inside of it that he can spin. So you can imagine you have this little turbine here that spins around. So we have a little turbine. So he does two things. One, he sits there for a long time and just cranks the turbine. What does he observe? Well, what he observes is, again, he's doing work, right? He's doing work. And what that does is, because of the friction with the water, right? You have turbine friction with fluid. And over time, what happens? The water warms and the ice melts. Easy enough to do. In fact, you do an experiment like this in the second or third rotation of CHEM class. So looking at colligative problems. There's another way to melt the ice. Right? The other way to melt the ice is just crank the heat up on the bath. This is the bath in the book. What happens? Well, all you're doing is generating heat, since not doing work. And what happens? That heat transfers into a green container, beaker. And what happens after that? The ice melts. And then he does nothing. Do nothing. And of course, eventually the ice melts, but slowly. Right? So what Joule observes, it seems very trivial, but this is a groundbreaking experiment at the time. What he observes is basically he tests everything, right? He's doing things with different speeds. He's trying to measure how much work he's putting in, right? He's doing all the due diligence, all the observational details, right? Think about the speed of the crank, or how the water temperature differential, how much ice is in there. He's doing all of this work. And what he concludes is that it doesn't matter how you apply the energy, the same thing happens. And no matter, and if you think about how much heat is generated from a flame versus how much energy is generated from a crank, he finds that no matter how much energy you apply either way, you get the same result. Right. So what he determines in a very, very, very obvious kind of experiment that he determines is that heat and work are the same energy, are made up of the same stuff. Right? So the thing that's being transferred from the bath or being transferred in and out of the beaker is the same stuff, regardless of how it's made up of the same material. And I mean this in a very kind of like abstract way. Same stuff. Energy isn't stuff. It's just a number. But it made up of the same stuff. Let me tell you, when he published this stuff, no one believed him. It took about 20 years, actually, until Boltzmann, which is the statistical interpretation of thermodynamics, which we'll do in a couple weeks, that people started to realize that he was correct about this. All right, so empirically, it wasn't obvious that he was right. They were convinced that Joule did it wrong. And of course, Joule wasn't a scientist. He didn't work at Cambridge or Oxford. He was a brewer. That's why he did all this stuff with water and stuff, is because he had all the brewing equipment and company. He was not a particularly talented scientist. He made beer. And of course, that's just a very relevant question for beer, right? And mixing, right? Or what's the most efficient way to generate heat or to warm up some slurry of your hops and your alcohol, all the crap and the yeast and stuff like that, right? And he shows that you can do it by using a flame, or you can do it mechanically, and you get the same result. And therefore, whatever heat and work are, they're made up of the same thing. Okay, so what he comes up with is a new equation. So he comes up with what's called the laws of thermodynamics, Joule amongst other people, which are a little different than the way that I've introduced things, but it's a traditional way. And what he says, what Joule says, is that the change in energy the du is equal to that the energy change is split into two parts. Now I'll label this with a special label. One is dq, the change in work or the change in heat, plus dw, the change in work. So this is heat change. And this is work change. All right. Now you might notice I used a really weird symbol here. This little cross. It kind of looks like the squiggly partial derivative symbol, but I've made a cross through it. There's a specific limitation with Joule's approach that is circumvented in Gibbs's approach that necessitates me to write this. These are not partial differentials. These are what are called, and I want to explain this graphically to you. These are what are called inexact differentials. They're different than a partial derivative. These are what are called inexact. One of the things that we discovered about Gibbs's equation, let's go back to it again. Gibbs's equation says that the change in energy can be directly related to the change in entropy, the change in volume, and the change in number. And these are dn's. These are regular derivatives. What that means is that the change in energy doesn't matter how we take a path along S. It doesn't matter what path we take. All it depends on is the beginning point and the end. So what I mean by that is this. So in Gibbs's formulation, what Gibbs is doing is he's plotting, very simply, I'm doing it in 3 dimensions again, a function, u, that is a function, say, of v and x. And we generate a surface, right? We can pick a different volume and a different entropy, and we get a different energy. And it's a singular function. So we get this like surface in 3-dimensional space. It doesn't matter. I'm just drawing some pictures. Little surface, right? And I can pick a point, right? My initial point on this surface. We'll say right here. Right? This is the initial u, the initial of my initial point, which is some function u of our initial volume and our initial entropy. And then we can pick some final point where the system is going to evolve. Maybe we're pushing and pulling, we're doing work, we're transferring heat. It doesn't matter, but we're doing something. And now I have some final energy, which is u of the final volume and the final entropy. And no matter which path I take, right? If you're a hiker going from here to here, you can go across many different paths. I could take a really long scenic route, or I could take a direct route. Right? I could go something like this, right? Directly. I could loop out around here.
As long as it's still on the surface.
Right, as long as it's, yeah, well, we can only be on the surface, but yes. But the idea is we can go any direction we want along the surface. Maybe you have a piston and you push it and pull it, and you go to an intermediate state, you go out further and come back, you just do a bunch of changes. But no matter what you do, you always come back to the same point. And what Gibbs's equation guarantees is that no matter the path, so Gibbs's equation is what we call path independent. It means no matter the path, du is always the same. So the observed energy that we measure, the change in energy we measure, is independent of the specific steps we take to go from I to F. No matter what, du is always going to be just the difference between this energy and this, independent of the path. Now, that's a different question than what path does the system take automatically. If we start at UI and it wants to move to UF, the system is going to take a specific path. It's going to choose the most efficient path to travel from point A to point B. That's not really what I'm saying here. What I'm saying is that if you physically put in energy or remove energy to take the system from UI to UF, it doesn't matter which path you take. The change in energy only depends on the beginning point and the end point. All right, we have a specific name for this. What this is saying is that this is what's called U here. So U of N, V, and S is called a half function or state function, different terms, same term, which means that any change of that value, it means du is only dependent on the initial and final values of the parameters, not the path, how you move through the parameters. Okay. Now, that maybe doesn't sound that interesting. If you guys remember the fundamental theorem of calculus, which is that the integral of a function, of a derivative of a function, is just the function evaluated at its upper limit and lower limit. It's the same, right? That the integral of a function doesn't really matter the path you take from point A to point B. It only that matters on the values at the beginning and end. That's the fundamental theorem of calculus. Same idea. That energy is also a path function. Now, what about Joule's energy function? Joule's energy function is a function of Q and W, work and heat, which again have very, very, very obvious interpretations in your head. One is physical motion, and the other one is whatever else heat is, but they're not associated with like a specific measurable, right? I can't say that heat is necessarily a function of volume or entropy. It's some combination of volume and entropy. Work clearly has something to do if we're compressing a gas. Obviously, volume is changing when we compress it. So you can think, okay, work has something to do with V, but it might also have something to do with S. So these parameters get kind of mixed up and jumbled up into a complicated morass when you work and heat.
Yeah.
And so what Joule has, in Joule's perspective, is he has the same function. He has a different function, but he plots it the same way. But his function is a function of work and heat, and the output is energy. And again, maybe you can do the same idea, do some process on a surface of values of work and heat. Surface like that. Right, and we pick 2 points, just like before. Here's use of I, and here's use of F. And now I can traverse this surface any way I want. I can do some work and then cool with some heat, remove the heat. I can remove the heat first and then do some work. Lots of different ways to do things. Lots of choices. I can go the most direct route if I want. I can go to the right and then kind of curve around the edge here and lead there. I could do some loop-de-loops and just go backwards and forwards through my space and end up in the same place. So I have different paths through this system. And it turns out that the total energy, which would be the integral of this path, so the total power used, total work used, would be the integral from UI to UF of our path. And depending on the path, this is not the same. So we pick path 1, and it turns out that when you integrate over path 2, from UF to the UI, they're not the same. Every path is different. So this is so what I could say is that U, the total change, let me call this delta U. The total change is proportional to going along this path and integrating. And it depends on which path we take. So work and heat, even though they're very, very easy to think about, right? You intuitively think about work, physical motion, and heat as heat. But when I parameterize my system as a function of work and heat to measure the energy, the total energy, in order to figure out how energy changes, I have to know the path. They're path dependent. So work and heat are path dependent functions. So if we want to understand things in terms of work and heat, we have to define the path we take. So this is the kind of dichotomy of our two approaches to thermodynamics. We have this very abstract one that Gibbs comes up with these 3 parameters that don't really seem obvious how we measure them. But it's a path independent. We know that if we can measure the energy at point A and we know the energy at point B, then we can always figure everything out. It doesn't matter which way we go. You can always interpret it using Gibbs's equation. But in order to understand how a certain process changes the energy in terms of work and heat, we have to know exactly the path you take from point A. So either we have to consider the path, and then we have an interpretable set of interpretable quantities that we can measure, work and heat, or we can have slightly more abstract quantities, but we don't have to worry about the path. Okay. So when we do engineering thermodynamics, when you're doing machinery and mechanics and things like that, work and heat is very useful because you're doing kind of concrete steps. You're expanding the gas, you're compressing it, you're heating it, you're lowering it. We'll go through some of these processes in class just to illustrate that. And I'll illustrate to you that it depends on how you go from point A to point B, changes the amount of energy. And energy is dependent on the path. But in chemistry, we're only going to care about delta S and delta V and delta N, right? That's stoichiometry and entropy or free energy, and change in volumes, expansion and compression. Those are things that we can measure in chemistry. And in chemistry, we don't really care about the path. What do we care about in chemistry? We care about the starting materials, we care about the products. We have some starting material. We don't really care what happens in the middle. Half the time we can't even observe it. So it doesn't really matter. So Gibbs's formulation is very, very useful for chemistry. Because just like chemistry, we want something to be path independent because we can't observe the path. We have no knowledge of the path, or it's very hard to not determine it. And so we want some sort of mechanism or some sort of framework to analyze our reaction that allows us to not worry about what's going on in the middle. That's what Joule gives us, or that's what Gibbs gives us. Joule does not give us that. So if you were to take this class of anybody else, they always start with Joule. But I don't start with Joule because we don't really use Joule in chemistry. We use Gibbs in chemistry. The things that Gibbs cares about are the things that chemists care about. Changes in molecules, changes in volume, changes in entropy, which will be related to free energy and equilibrium. So those are the things we care about. Let me pause for a second. Any questions? That was a lot of conceptual talking. So let's apply it to something. So when you look at things from Joule's perspective, you ultimately, the idea of using working heat is very convenient. But we need to choose the way that we make a path very carefully so that we can simplify, we can make the analysis path independent. And so there's some simplifications we can make to our systems that will take Joule's equations and give us something that's path independent, some simplifications. And we'll think of it as this analysis from Joule's perspective and Gibbs's perspective. It gives us the same result, which is a slightly different point of view. And so what we're going to do is we're going to start thinking about this box, this very generic box we've constructed, and we're going to put it in environments that are much more common and constrained in science. Right? We're going to constrain some of the parameters and see how that the system then evolves, how the analysis simplifies. And what it comes down to, ultimately, chemistry, thermochemistry, the knowledge of how chemistry generates heat, absorbs heat, does work, ultimately comes down to understanding thermodynamics in very, very small, constrained environments. Certain set of constraints that we often use in chemistry, that 99% of chemistry is done. And so what we'll do for the next couple of classes is go through those constraints. Common boxes, if you will, constraints for our boxes that we see in the lab every day. And the first one I want to talk about we'll call this constrained thermodynamics, which means that not everything can change. We're going to assume something to be constant. And the first one we're going to talk about today, or this week, are what are called isothermal processes. Right? What is isothermal? Well, iso in Greek means same. Thermal means heat. So these are processes with the same heat at all times. And the condition that we choose, therefore, is our most convenient one. Delta T is equal to 0, right? So what we're going to start with is a box whose temperature is always fixed. Right? Of course, we do this in chemistry every single day. Isothermal conditions. We often mix and match it with other things, but if you ever do anything in a water bath or a hot bath or an oil bath that you set the temperature on, you're doing isothermal chemistry. So you have an intuitive idea of what an isothermal process is. It's doing a reaction at constant temperature in a bath. So let's just draw that, right? Our box now, we have to now adjust our box a little bit because now we're going to put it in a bath. So I'll put my big old dish. There's a big old Le Creuset dish full of water, like a Dutch oven. And what I'm going to do is inside of it, place my box, right, with some particles in volume. First, I'll put my box in here. I'm not going to fill it just yet, but I'm going to cover the outside. Right, I'm going to fill the big thing with water. Right, and I'm going to set the temperature of the water to some fixed amount. Right, so it doesn't matter. We'll just call it the temperature of this is T bath, and that dt is equal to 0. Okay, so that we basically have this on a hot plate. Right, it's on a hot plate with a temperature. And then I'm going to modify my box, right? It's still a volume. It still has N atoms. So I have some atoms in here. Also, I still have N atoms. And I still have volume. Still have some volume. It's still a fixed box. But what I'm going to do is I'm going to change the walls. Instead of them being closed and sealed, I'm going to allow them to transfer heat. Right? So I'm going to draw that. I'm going to draw a little to indicate that my box allows the transfer of heat. I'm going to draw a little squiggly orange to indicate heat transfer. So like that, maybe. And I'll give it a name. We have a name for something that allows heat transfer. This is what's called a diathermal box. All right, so what does that mean? Well, that means that heat can transfer through it. So the change in heat is not equal to 0, but you can't transfer molecules through it. All right, so dN is equal to 0. Right, so it's not a porous box, but it's a sealed box that, like a realistic box, right? Because you can have a sealed container, but like for instance, this watch is waterproof to 100 meters. It's sealed to water, but it's still going to change temperature. It's still going to change heat because it's metal. But there's no exchange of air between the interior and the exterior of my watch. Right, so my watch is a diathermal box, it's sealed but not. Okay, and inside of this box, I'm going to put a piston again. That I can move myself.
Wait, the box on the inside is a gas.
Yes, it's a gas. And inside of that box, I have a piston I can move left and right. Little piston. Okay, so let's think a little bit. Let's write down an equation of state for this system, right? Using Gibbs energy, right? So let's think from the perspective of the box. So maybe, for instance, we put the box in and it's not at the same temperature as the bath. Maybe it's colder or warmer and it's going to exchange heat. And it's going to exchange heat PdS minus PdV plus mu change in molecules. So what's going to happen when I put this box with a piston? Well, if the temperatures, so what's going to happen? Well, if the box is at a different temperature than the bath, then some heat is going to exchange between the bath and the box, right? So we're going to have some change in heat. But as you remember from our previous example, and yet last class where we had the partition box, the piston, that the two boxes were at different temperatures, the piston moved. And the piston stopped when the temperature between the two compartments was the same. It's exactly the same case here. So what's going to happen is that some energy is going to flow into this box, and it may generate some entropy by heating the system up and making things move more randomly. But it also might shift the volume as well by moving the piston. Right, so but the other one's not going to change. dN is 0 because there's no molecules can't leave, right? So it's a sealed box. But the important thing is that imagine now, right? So the two ways that the energy can change is you can change the volume or you can change the entropy of the box. All right, so again, let's think very, very clearly. Think about Gibbs's, Joule's perspective, right? Joule says, this is Gibbs. Joule says that du of the box is equal to the change in the heat plus the change in the work. Right? Now let's compare these two. Right? Now it seems maybe it's more, right? These are all energy is the same, so it doesn't really matter how we talk about it. We can call it work or heat, we call it entropy and volume. But now we can see a correlation between Joule's and Gibbs's relationship. They have two terms that control the energy. And one of them is a constructive motion, which is work, right? The piston is moving back and forth. That's a constructive motion where the energy is being applied. And then we have everything else. Right? So we can immediately relate minus PdV with work and TdS with heat. I haven't done any math. I'm just comparing things, right? But already we have kind of a intuitive idea of what changes in volume versus change in entropy are by the motion analysis. And they correlate exactly with heat and work. Right? And so we'll come back to this next class, but there's very clearly a direct relationship. I don't know if you can see that well. I'm sorry, you can't see that. Yeah, the glare is really bad. Is that better?
Yeah.
Between, sorry, heat, Q, and entropy. Right? They seem to be associated with the same thing just by deduction. And work has something to do with volume change. We'll come back to this in relationship. Entropy and heat are directly connected to each other. They measure the same thing, but in a slightly different way, but they effectively measure the same thing. And so that's kind of the connection, right, between Joule and Gibbs, is that entropy is a measurement of heat. But the important thing, the thing that you should realize very carefully here is that it's not guaranteed that 100% of the heat is just going to be entropy. It turns out that it might have some heat generated from volume motion, maybe because there's friction. Well, it's a complicated balance, but in a very simple box, where things are fixed, we can kind of get a relationship between these two terms. That heat has something to do with entropy and vice versa first. And we'll see that very clearly. Okay, so now let's try to work this problem out a little bit more. All right, so if the box is hotter than the bath or vice versa, it doesn't matter. Let's just say there's some temperature differential between them. Heat's going to flow in and flow out, depending on which one is preferred. But even though heat's going to flow in and flow out, we're at constant temperature. So if heat's going to flow in from the bath into the box, that's going to raise the temperature, but the temperature can't change because it's constant temperature. So any energy coming into the box has to come out of the box as well. So the total energy change of the system, so the total energy change has to be zero, which implies that the change in the energy of the box, so that's supposed to be a U, has to be equal to minus the change in the energy of the bath. Right, because you can't raise or lower the temperature. Okay, so any heat that flows into the box to warm up the box, some excess energy has to come out in some way to equilibrate. Total energy has to be. So what that means is that in some sense, if the bath brings in heat, right, the system has to compensate for that added heat by removing the energy. Well, if it removes it as heat, then you haven't done anything, right? If you brought in a unit of heat and then you release it, then you haven't changed it. Right? But what you could do is that if you bring in a unit of heat, you can displace that energy by using it to move the piston, right? So you bring in a unit of energy and then use it to move the piston. Bring in another unit of energy and move the piston, vice versa. Or maybe you use the piston moves and generates some energy in the box, and then the box gets rid of it and gives it to the bath. All right, so there's an inner conversion between work and heat. If heat comes into the box, work has to be done to get rid of it. If work is done in the box, heat has to be removed to get rid of it, and vice versa. So what we can say, therefore, in the box is that du box has to be equal to 0, which means that PdV is equal to TdS. So any heat that comes in has to go out as work and vice versa. There's always a balance between these two energies. Now, this is an interesting equation. We can do a little bit of calculus if we can learn something really interesting. The thing that we don't know yet is if let's hide the right-hand side, let's look at the left-hand side for a second. We don't really know the relationship between V and P yet. Okay, but we do have one in our heads, right? Which we have Pivner, right? We have Pivner. We can relate pressure. We know how pressure and volume are related in an ideal gas. So what I can actually do is take this equation and apply Pivner to it. And let's see what we learn from it. Right, so what we're going to do is assume an ideal gas. And what can I say about an ideal gas? Well, I can say P is equal to nRT over V. So let me make that substitution into my problem, my equation for my system. Now I have nRT over V dV is equal to T ds. Now I can get rid of the T's, right? A T on both sides. I can cancel the T's out. N, of course, is a constant because we have a fixed number of moles in the box. R is a constant. It's the gas constant. I think I've mentioned it already. Maybe I'll write it down in a second. And so what do we have? Well, if I rewrite this just a little bit, I have nR dV over V is equal to ds. Now I have on both sides of the equation a small little exact derivative, right? I've got some little chunk here. And what I can do is I can integrate that chunk, right? If I say that the small chunk change in entropy is equal to the small change in volume times some function of volume, I can figure out how the total change in entropy by integrating both sides. So let me add an integral sign to both sides. Integrate both sides. And now what I want to do is I want to integrate from my initial point to my final point. On the left-hand side, we could write, you integrate from, like, say, V sub I to V sub F. And then we could write S sub I and S sub F. Right? We go from the initial point to the final. Integrate both sides. So now I can look at the total change in volume and relate to the total change in entropy. I'm going to go ahead and I'm just going to copy this over to the next page so we don't lose it. Just need a little more room. So let me just clean this up a little bit. N and R are constant, so I can integrate, I can just bring them out with NR integral from VI to VF of dV over V is equal to the integral of SI to SF. Yes. So let's just integrate this out. What's the integral of 1 over V or 1 over X dx? Do you remember?
Natural log of 1.
Thank you. Or natural log of X. Right. So the integral, this is the integral of 1 over V. It's log of V. And then what's the integral of, well, this is the integral of 1. What's the integral of 1? It's, yeah, it's X. So it's S. Yeah. Right. So the left-hand side, applying the fundamental theorem of calculus, says that NR log of VF minus log of VI is equal to SF minus SI, which of course is just delta S. And we can use a log. These will become very handy in the problem set this week. Let's use our log rules. There's lots of logs in this class, so get used to them. Log of X plus log of Y is equal to log of the product. The difference of logs is equal to log of the quotient. And ln of x to the y power is equal to y times the log of x. Right. There's some algebra 2 for you guys to remember. We use these a lot in class. As you can see, log appears immediately. The first problem we do, logarithms automatically appear. We're going to see logarithms in this class a ton for this reason. And so I can apply the second log rule here. We have a difference of logs. So this says that delta S is equal to NR log of the ratio of the volumes from the initial to the final point. This is for isothermal. This is a compression or an expansion, right? Because we're changing the volume. Voila. We now have an actual equation for entropy. Right? We've made a very, very small approximation. Put the system in a bath. What does that do? It defines a temperature. We've now equilibrate our box to a bath. And now we have a fixed temperature. When we have a fixed temperature, that simplifies the way energy flows in and out of the box, which simplifies our math, gives us a constraint, and out of that falls a very, very simple equation for the entropy. Like, entropy is a well-defined concept that we can measure if we can define a temperature for the system. Temperature gives us a connection, physical connection to entropy. We can define a temperature for a system, we can measure its entropy. If we can change the temperature of a system or change the entropy, we can also measure it. Right? But this gives us now an absolute reference for entropy. Right? If we have an ideal gas, we know how many moles we have of it, and we can measure the volumes, which of course is simple. You just need a ruler to do that. We can always measure the entropy exactly. Right? So entropy and temperature are intricately connected. Right? And defining a temperature, fixing temperature gives you a direct connection to entropy. It's a result of the system. It is a product of the system's variables. So defining temperature gives us an absolute reference for entropy. And what we're going to see, I think next class, maybe the class after that, is that this is a two-way street. That we can come from it experimentally, which is we define a temperature, an empirical temperature, and that gives us a way to measure entropy absolutely. It turns out if you define an absolute reference for entropy, meaning that you define what zero entropy is, what does it mean to have zero entropy? Then you can also define a temperature from that as well. So it goes back and forth. So temperature and entropy are intricately connected. We've already seen that multiple times, and what we'll do next class is formalize that connection. That's where we're at today. And I'll see you guys on Thursday. Thank you. And I'll post today's video as well when I get a chance, probably tomorrow.
That's so funny. Alrighty. See you on
See you Thursday.
Thursday.
I think it's funny that you interviewed the OU because that's literally the complete opposite side of